Okay, let's get started. Uh, Welcome everyone. So we looked at Bitcoin and its fundamentals, Merkle trees in the last couple of classes. And today we will look at some of the other proposals for cryptocurrencies. I saw many of you were in Silvio's talk today, so that was great. Yeah, we will look at proof of stake and we will look at a couple of other proposals. So I did talk about some of the limitations of Bitcoin in the last class. So perhaps the biggest, or definitely one of the biggest limitations, is that of scalability. So in Bitcoin, there's a fixed upper limit on how big a block can be. The block size is fixed to be 1 MB. And then, of course, that limits the number of transactions that you can do every block, which is roughly every 10 minutes, right? So one very obvious proposal is to just increase the size of the block, right? What about making the block size 5 MB or 10 MB or something like that, right? So that is great, but unfortunately, there's a problem with that. And the problem is, if you increase the size of the block takes longer to propagate, okay? Which means that essentially, when you solve a puzzle, it takes longer to propagate the puzzle. And that also means that basically there are more folks in the system, especially if you are an honest party. So blocks take longer to propagate. Which essentially means that, let me draw a picture here. Suppose somebody did end up solving the puzzle, which is the next block. So this is the next block somebody mined, but maybe it takes now longer. And in that time, honest parties are still working on this block, which leads to increase in the number of folks. And note that even if you are using Merkle trees, you need to look at the entire block to validate it, right? Maybe the puzzle solution is correct, maybe the hashes are correct, but maybe there's an invalid transaction in the block. And in that case, the block would be considered invalid. So that's why honest parties need to download basically the entire block and then need to check for themselves if the block is valid or not. But on the other hand, maybe the dishonest parties are better connected. Better connected or better coordinated. So in that case, dishonest parties don't waste that much computing power. As soon as one of the dishonest parties is successful, they can very quickly signal to the other dishonest parties that you can stop mining here, and here's the next puzzle on which you start mining. And that's why, suppose there are two folks. Suppose here we have honest, and let's say this fork was mined by some dishonest party, but maybe at a slightly later point. And now all the honest parties jumped here because this came first. But then again, we will see many forks. So essentially, the computation of the dishonest parties is not so coordinated. On the other hand, if the honest parties are able to coordinate their computation better, they can have less forks but a longer chain. Okay. So even if the dishonest parties have less than 50% computing power, maybe that's enough to control the longest chain and to produce the longest chain. And that's very dangerous because you are able to launch a 51% attack with less than 50% of the computing power. And in that case, you can go back, you can erase the history, you can rewrite the history. Basically, the security of Bitcoin is completely broken in that case, right? So the problem here was, even if you have less than 50% of the computing power, because you are better coordinated, you don't waste it in the forks. You focus on a chain, and that chain keeps getting longer and longer, right? So this is a problem. This means that in some sense there are problems while talking about the scalability of Bitcoin. Making Bitcoin more scalable is not as simple as just increasing the block size of Bitcoin. So there's a proposal to overcome this. This is known as Ghost. And this stands for greedy, heaviest, observed subtree. And we will see what it means. And in fact, this proposal, I think it came in 2014 or 15. And since that, it has gained quite a bit of acceptance. And in fact, a variant of this is going to be adapted by Ethereum. And that variant is known as Casper. And the name is kind of, there was a movie in the 90s where the name was Casper, which is a friendly ghost. So that's how they derived the name from this word ghost. Okay, so here let's go back to the problem of scalability. So you see that if the dishonest parties are successful, they will have a longer chain but with less forks, right? On the other hand, honest parties might have a lot more forks but a smaller chain. Okay, so why choose the longest chain? Why not choose a chain which might have a lot of forks but maybe shorter? A lot of folks in some sense show you that more computing power was invested in this branch as opposed to this branch, right? So here you can see more computing power. So now the new proposal is, rather than choosing the longest chain, you choose the chain or you choose the branch which has the evidence of the most computing power being spent on it. Okay. So here in Ghost, choose the heaviest subtree. So even if some honest party produced a fork, the fork eventually died down. That fork still plays a role in determining whether this particular chain or this particular tree is selected or not. So the idea is that here, let's say there are two competing subtrees. You just look at the number of nodes here versus number of nodes here. And you count all the nodes, even in the forks. And whichever has the maximum number of nodes, that shows the maximum amount of computation. And that's what you select. Okay, so the rule of thumb is something like the following. The first rule is heaviest subtree is the right one. And if there's a tie, then you go to the second rule, which is the first subtree is the right one. Okay, and if you are working on a subtree, but you see that there is another subtree which became heavier, you are supposed to switch to that. Okay, and just keep in mind that there is still a main chain. So for example, if this is the heaviest subtree, maybe here we will have a chain. So just for simplicity, let me extend this one. So there's still a chain which is represented by this chain in green. And that is still the main chain. And only the transactions which are present in this chain are considered to be valid transactions. Why can't honest nodes be working on a subtree forked by a dishonest node and making it heavier? Yeah, that can completely happen. I mean, if the honest node generally produces a subtree which is the heaviest and also the first one, then of course all the honest nodes should switch to that, right? So in Bitcoin, we don't try to prevent honest nodes from mining any block. So of course you can, even if you are dishonest, you can mine many blocks. Just we don't want dishonest nodes to take over the entire network. Then can't an attack happen like this without 51% attack? No. I mean, in this case here, what does a dishonest branch mean? A dishonest branch means that it did not conform to these rules. Either it's not the heaviest, or maybe there's a tie, but it was not the first one. And in that case, majority of the computing power will go to the honest branch, and that honest branch will get heavier, if not the longest. Okay, so there's still a main chain, and only the transactions in the main chain, they remain valid. The transactions in the forks, they are not counted, even if forks determine which chain is considered to be valid and the longest. So how do you decide the main chain? What is the algorithm for deciding the main chain? You start with the genesis block. And then at every step, maybe you encounter multiple possibilities. So for example, let's say here, you see 3 possibilities. You just see which one is the heaviest. At every step, choose the heaviest. And you keep doing that recursively. And eventually you will end up at one of the leaves, and then you have sort of marked the main chain. And if there's a conflict, then basically right now we have a fork. Hopefully the fork will be resolved eventually. So last time in Bitcoin, we saw the nice property that a long chain tends to get longer and longer, which is a very nice stability property. So even here we will prove, or it's a simple observation rather. The observation is that the heavier subtree becomes more and more heavy. So this is a very nice stability property, and this is sort of easy to see because of our two rules, right? Earlier, if there was a conflict, the miners were divided across two different subtrees. Just at random, one of them will get extended, and then that becomes the heavier one, and then all the honest miners would eventually switch to that subtree. And then because honest miners control 51% of the computing power, that subtree becomes even more heavy. And the other subtrees sort of die down or fade away and things like that. Okay? And the nice thing here is that another observation, the honest nodes or the honest miners, they no longer waste computation because of forks. Because every fork plays a role in determining which subtree is the heavier one, even though the transactions themselves in that fork do not count. Okay, so just keep in mind that all valid transactions are still in the main chain. Forks just tell you which path to take, which chain is the main chain. Okay, so this is the ghost proposal, and Ethereum is adapting a variant of that, which is called Casper. And in some sense, it makes progress towards solving the problem of scalability. Any questions?
Can I ask a question about that?
Yeah.
So in like a scenario where someone has completed like they've solved a puzzle, but after the fact they realize that someone has already solved the puzzle before them and they are the first person to make the next block, is there any incentive for them to report their solved puzzle to like weight the main tree more versus just trying to start to solve the next puzzle? Like, do they get like a small reward for reporting their late puzzle?
Yeah, that's a good question. So I think again it depends on the details of the proposal. I don't know what Casper does, but what is the incentive for them? So one incentive for them would be to make sure that the subtree which they are working in remains the heaviest subtree, and you don't suddenly switch and go in a completely different universe. So that's one. And other one, yeah, I don't know, maybe it does make sense to give them some kind of reward. Yeah.
And think about waiting the subtree there, and that makes sense. Thank you.
Mm-hmm. Yeah. Any other questions?
I have a question.
Yeah.
So over here, it seems like the dishonest uh, nodes, even if they don't have 50% computation power, they can get a heaviest subtree. Like, assume that there is a fork, and
Mm-hmm.
then all the dishonest parties start to find the next block on top of a single block. Like, there can be many hashes which can be put on top of a single block, right? And they decide that instead of just putting in one block, they will find many blocks, and then they are essentially making a subtree heavy, right? Like the
But the
honest
point is that if they have less than half of the computing power,
Mhm.
if all the dishonest parties are working in one subtree and the honest parties are working in another subtree, then the honest subtree is going to win.
I don't think so, because in the honest case, we are assuming that after every new block, everyone starts to try building on top of it. So everyone starts a fresh computation. Whereas the dishonest parties can choose not to start a new computation, just try to find many blocks, many different blocks which can be put on top of a single block. So they are not wasting any computation of their own, right?
Oh, I think maybe what you're asking is that if I continue my computation which has failed so far,
Yeah,
as opposed to starting a new computation, I have a better probability of winning.
exactly.
No, that's not the case. I mean, if you have failed so far, you continue this computation versus you start computing on something which is completely different, it's not going to make a difference. Because every trial, every time you hash, the hash just sort of gives a random output. Um, your probability of success in that output is just determined by this parameter k.
But you have already got past some of the cases which are not the right ones, right?
Yeah,
So,
that does not increase your probability of being successful in the cases which you have not tried.
okay,
Yeah, this I mean the fact that you failed in the past doesn't make it more likely that you will be successful in the future.
okay,
Every trial is independent because every time the input to the hash function is different, right? You choose a different nonce versus you choose a different nonce and a different block. Doesn't make any difference.
okay.
Okay, good. So let's continue. So another proposal to deal with this scalability problem, and also it relates to the cost of the transactions in blockchains, is, let's just call it, inclusive blockchain approach. So they are targeted towards two points. So one is scalability, and the second is they're trying to keep the transaction costs lower. And here the idea is that so far we always discard the forks, right? And that is important in some sense because what is there in the forks might conflict with what is there in the main chain, and we have to choose one, right? But now the point is that maybe there is some information in the forks which doesn't necessarily conflict with the information in the blockchain. And in that case, why should we discard that information, right? Why shouldn't fork have some useful information? So let's say, I don't want to pay a significant transaction fee. I'm some small guy, I'm willing to wait a few hours to make sure my transaction goes through in the blockchain. Then I broadcast my transaction, and maybe at least in one of the forks, my transactions might appear, maybe not in the main chain. And in that case, as long as it doesn't conflict with anything in the main chain, it should stay. It should be considered to be a valid transaction. And this is exactly the proposal in case of inclusive blockchains. So there are still some questions like, what if the main chain gets extended later on and a conflicting transaction appears in the main chain? Then what happens? Does the fork get erased? If so, then forks can never be trusted, and we are back to the old proposal. So here the idea is that we look at the current state of the blockchain and we look at the current state of all the forks. If there are transactions in forks which don't conflict with the current state of the blockchain, we keep them, we make them final. What that means is that from this point onwards, any extension to the main chain will be forbidden from involving any conflicting transactions. And that's why the transactions in the forks can now sort of be finalized. So in more detail, here's the proposal. So suppose there was a fork at this point, but then this became longer. And suppose there's some transaction, let's say TI here, or and this is the current state of the system. And suppose TI does not really conflict with anything which is in any of the blocks in the main chain. Then when you are trying to mine the next block, you will look at this block, and the puzzle that you will try to solve is you are mining on this. This is your puzzle, but you also take this block. So let's call this block BI. This is, let's say, block BJ. Your puzzle will be BI concatenation BJ in some sense. And then the remaining things like your information, your nonce, your public key. And this should be some K0s. So the rule here is that the next block on the main chain certifies all childless nodes which have not been certified so far. Okay. And what are the childless nodes? Of course, there's a node in the main chain, which is sort of the last one. There's a node here in this fork. So you take both of them. Maybe there's another one here. You will take this as well. And the next node, in some sense, certifies all of them. And automatically this means is that, what this means is that if there are non-conflicting transactions in these forks, they are considered to be valid and part of the blockchain. And now maybe this node gets extended, and maybe the main chain will get extended, and then this next block in the main chain will certify this block as well. Okay, so the idea here is that you can mine on the forks and hope to get them included. And then the miners on the forks, they are also paid some transaction fee, which might be much smaller than the transaction fee, which is paid for the main chain. Okay, and this is nice. This is inclusive in the sense that in Bitcoin, if you're a miner, it might be several years before you are successful in mining the next block, just because there's so much competition. But now in this proposal, you can go to any forks, any long abundant fork, you can try to extend those forks. And you can try to include new transactions, and hopefully there would be a block in the main chain which would certify that fork or that extension of the fork which you created, and in that case you will get paid, the ledger will be extended, and there'll be new transactions which are now included for very little transaction fee.
So like a new block, the new coin that comes only in the main chain, not in the side chain. The new coin that comes.
Yeah,
Okay,
yeah, I mean, so both options make sense, right? If you wanted, you can have a much smaller number of coins created in the forks as well. But I think the cleanest proposal would be that new coins are only created in the main chain, and in the forks, sort of the chain is extended only based on the incentive of the transaction fee.
okay. And like nobody can do any fraud because if I have 10 bitcoins and if I need to transfer to someone, they need my secret key.
Yeah, that's always the case.
Okay.
You always need to sign your transactions. But there's another point here, right? Maybe there's a conflicting transaction. Maybe let's say Alice has a single Bitcoin. In the main chain, Alice transferred this Bitcoin to Charlie, and in the fork, Alice transferred this Bitcoin to Bob. So then we have a conflicting transaction here. And then the transaction in the main chain will take precedence.
No, but will won't it happen like this that because the side chain has a conflicting transaction, will never add this side chain in the main chain?
No, I mean, there might be many transactions, some of them conflicting, some of them non-conflicting. So you just add this block to the, I mean, so the block in the main chain will certify this block, and automatically all the conflicting transactions are considered to be invalid.
Okay. So it's like even if the side block has wrong transactions, we still certify them.
Yeah. But that doesn't mean that all the transactions in that will be valid.
Okay. Thank you, sir. Thank you.
So this leads to a structure which can be seen as a directed acyclic graph. Or a DAG. Okay, so here we had a tree, here we have an even more advanced structure which is directed acyclic graph. I'm sure that you can come up with other structures and they might have some nice properties. Okay, any other questions?
So I have a question. Uh, when we are mining the new block on the main chain, suppose the side chain contains BJ and one another block on top of that. So it will certify both of them.
Sorry, say that again.
So suppose the main block that we are putting in, that will certify BJ And suppose if there was a block on top of BJ as well, so will it certify both of them or only one at a time?
So it just certifies all childless nodes,
Right.
which in particular means that the last node in every fork is certified.
Okay, so it will.
And once the last node is certified, all the previous nodes are certified automatically as well. Because the last node, in some sense, certifies the node before that, which
Right.
in turn certifies the node before that, and so on.
But then this can lead to a change of the main chain, right? Or not?
What do you mean?
I mean, the main chain can switch to the one, uh, the, the side chain containing BJ, because in the main existing main chain we are adding one block, but the side chain gets two new blocks added and certified.
Why two new blocks? So suppose BJ was the last transaction, and there's this. Suppose this was the main chain and this was a side chain, and then we have a new block mined.
Yeah, so I'm saying suppose there is a BJ
Then main
plus
chain gains
one,
by one, and the side chain also gains by one, right?
and suppose if there was another block on top of BJ, which is BJ plus one.
Here,
Yeah.
okay.
So now the side chain is certifying BJ plus one, right?
So here's the block BJ plus one, and this is the main chain.
Right. So the
That automatically means that this chain is longer than this chain. And now both of them are extended by one. So the
okay,
main chain still remains the main chain.
okay, all right, yeah, that makes sense.
Okay, so one small question. Once like the BJ plus one is certified, I can never add one node on top of BJ plus one.
No, you can. That's the whole point. So you can go to BJ plus 2. BJ
Okay.
plus 2 is not certified by at this point, but if the main chain gets extended, then maybe the next block will certify BJ plus 2.
Okay,
So
okay.
that's
But
why you can
like,
continue mining on every fork. You can even create your own fork from any point.
why are we drawing an arrow from BJ plus one to the main chain? Just because it is being certified by the main chain.
Yeah.
Okay, okay. Thank you.
And there is an incentive for the miner in the main chain to certify all the childless nodes, because that miner can now collect the transaction fee from all these nodes.
No, but transaction fee will go to the person who mined the side chain nodes, right? Or the main chain person will get the transaction fee.
It will be split
Okay,
between
okay.
the two. So far, everything which we have talked about relates to proof of work, right? In proof of work, you have a computational puzzle which you are trying to solve. Uh, there are many miners which are trying to solve the same computational puzzle simultaneously. And that leads to a significant wastage of computational resources as well as electricity, right? So in fact, it is known that Bitcoin is using more electricity than, for example, Switzerland. And why? For this apparently useless computation, which is just hashing on meaningless numbers. So this computation is essentially useless to the mankind. It's not like we are doing some DNA sequencing or we are doing genomic analysis. It's completely useless beyond the purpose of just maintaining Bitcoin, of course. So now the question is, can we have a better, more green, a cheaper alternative to Bitcoin? And one of the proposals is based on proof of stake. There are many suggestions, of course. Proof of stake is just one of them. So in proof of work, your voting power in the system is proportional to the amount of computation that you have, right? The more computation you have, the more likely you are to be able to mine the next block. In proof of stake, the voting power that you have is proportional to the number of coins that you own. There's also other proposals like proof of storage. The bigger your hard drive is, the more your voting power is. There's also proof of memory, which talks about your short-term memory and so on. So proof of stake is a nice system in the sense that the system is less wasteful. You don't need to solve any meaningless computational puzzle. You don't need to use a lot of electricity. It relies on cryptography, and it is very attractive in some sense because it's a more green alternative, and it has its advantages and properties which Bitcoin doesn't, but it also has its problems. So many people present proof of stake as sort of a clear improvement over proof of work, sort of the next generation of blockchain. And in my view, at least, that is not the case. So one common criticism of proof of stake is that the more stake you have, the more power you have. You have more coins, which means that you are more likely to be able to mine the next block, which means that the new coins which will be created are more likely to go to you. But it's really up to you whether you consider this criticism to be valid or not. I mean, even in proof of work, right? The more money you have, the more computers you can buy, which can give you more Bitcoins, right? This is essentially how our society works. The more money you have, the more you can get. Sort of the problem of rich having more power and they are becoming richer and richer. So probably cryptocurrencies are not any different from that. Okay, so another problem with proof of stake is that it's much more complex. So maybe let me list an advantages and disadvantages. Advantages is more green. Disadvantages is it's more complex, definitely more complex than Bitcoin, for example. In fact, I will not be able to present any proof of stake system to you in this class. I will just try to give you some high level ideas. Let me look at the questions. Okay. More centralized, maybe some people consider this as a negative. I'm not so sure because it's a problem in proof of work as well. Okay. So how do you mine the next block in a proof of stake system? That's the question. So there are various options. First option is maybe the person who holds the largest number of coins will mine the next block. But that's not something which we want, right? Then the system essentially becomes centralized. And then basically you have a fixed person which will basically mine every single block from this point onwards. So it's clear that there has to be some randomness involved. And in proof of work, this randomness came from the computational puzzle. You try random inputs. Sometimes I succeed, sometimes you succeed, and so on. And my success probability is proportional to my computing power, right? So here what we need is your probability of success should be proportional to your stake in the system. Okay, stake is how many coins you have or what percentage of coins you own. And yeah, and how do we make sure that this happens? If there was a trusted third party, that third party has a record of how much stake everybody has, then the third party can flip a coin in that according to the weights and declare the winner. But of course, we don't have any trusted third party here. So in some sense, you need a decentralized mechanism of coin flipping so that the probability of success of any particular public key is proportional to the stake which this public key holds. Okay, and the way this is achieved is in every round or in every block, every public key is assigned some sort of score. Okay, so your score should be proportional to your stake times some random number or some random ID. Okay, and this function can be any function. It can even be the identity function. So maybe for simplicity, let's just assume that your score is equal to your stake multiplied by some random number. And this random number is coming from some domain, let's say 50-bit random number or something like that. Okay, and now the question is, how does one select this random ID? This random ID is of course different for different parties. Depends on your public key. Okay, so let's see. Random ID generation. And this is probably one of the most complex parts of a proof of stake system. So let's have several attempts. And maybe I will ask you why a particular attempt doesn't work. So maybe the simplest attempt is so every party chooses their own random ID. How about that?
Dishonest parties will always pick the highest number as
Yeah.
the random ID.
Yeah, so this just completely fails. Right? It is in your interest to pick the largest random ID because that maximizes your score. The second attempt is we don't want the parties controlling their own random ID. On the other hand, we want them to be able to compute that random ID. Okay. So maybe random ID of a party may be equal to some hash function applied on the block index. This is to make sure that random ID for different blocks is different. And let's say their public key. What about this? Public keys are cheap. sure, but why is that a problem?
Like if it is like this, that I will never be able to gain more points, right? If my public key is very bad,
Mm-hmm.
like
Yeah.
always
So
you
you
will win.
can, yeah. So there's also an answer in the chat. You can pick a bunch of public keys and you can maximize your random ID. But now the problem is if you pick a bunch of public keys, then you don't have, probably most of them will have stake 0, right? If you, or if you distribute your stake across multiple different public keys, it's not necessarily the right strategy for you.
No,
Right.
but
So what,
I'm trying to say that if one public key has say very high hash, then they will be the one who will be keep winning, and it is essentially like a centralized system.
but it's only for a particular block, right? For the next block, maybe another public key will have a high hash.
Maybe then the stake thing is not very well used in this case. If it is like
Well, you always multiply the random ID with the stake later on.
right, right.
So your score is always your stake times the random ID, and we are just talking about how to generate the random ID. So I think we are making progress towards an attack, but still there's one more idea required to defeat this proposal. So what is the problem? So the problem is here, I think many students were already going in the right direction. That's that it's predictable. Far into the future, I can compute, I'm just taking block index here. So I can pick a million different public keys and I can see for which block, which public key is the best. So let's say for block I, um, say for block I have some public key pkj, which is the best. And I can do this computation far into the future, a lot in advance. Then what do I do? And then you transfer your stake to this public key pkj just before block I. Okay. And then you can sort of optimize every block, or maybe every other block, if you assume that it takes one block to transfer stake.
Like, can we include the transactions also in the hash? Then probably this might not.
Yeah. Yeah, that's the next attempt. What about your random ID is hash of the last block and your public key pk. So this is attempt 3. It's better than previous one, but there's a problem with this as well. Any thoughts? So here the problem is that the person who is mining the current block has a lot of power. Because just imagine that if you're able to decide the last block, let's say you win once, right? Sooner or later, adversary gets to win. And then adversary can carefully engineer this block to make sure that in future, one of the adversarial public keys will keep winning. Okay, so you have some degree of freedom in deciding the last block. You can compute the hash for your public keys as well as for adversary, as well as for honest public keys. So compute hash for number one, adversary public keys, and second is honest public keys, and then see how it's playing out. If this block is favorable for the adversary public keys, you keep it. Otherwise, you try with a different block. And in fact, even here, you can even generate like millions of different adversary public keys and make sure you transfer your stake. So again, here the problem was predictability. Maybe you can't predict far into the future, but you can predict all these random numbers for the next block if you're mining the current block. So here's the attempt for, it will be the final attempt for this class, but it still is not ideal. This attempt sort of takes away the predictability property. So your random ID is the hash of, in some sense, your signature on last block appended with your public key. Okay, and now you can see that adversary cannot compute random ID of honest parties. So first you need to sign the last block, and if you don't have the secret key, there's no way you can produce the signature, right? So if I am the adversary, let's say I am mining the last block, I cannot really compute the signature of any of the honest parties on this block. And hence, I don't know what their random number is going to be. I can still compute my own random number. Okay, so this is still not entirely satisfactory, because even though I cannot compute your random number, I can still try to sort of maximize my random number by engineering the last block. And the way that attack is dealt with is that there's actually a committee which decides the last block. There's not a single individual which picks the last block. So there are many questions here. We are oversimplifying things quite a bit. The question one is, say the public key having the highest score is offline. So what happens in that case? Right? And it's not as simple as saying that, oh, hey, if this public key is offline, then you go to the next best score. It's not as simple as saying that, because I don't know who is offline and who is online, right? Maybe the miners wait for like 10 minutes. If there's no response, then they move on to the next public key. Then they wait for another 10 minutes. Then they move on to the next best public key. This will take a while, right? This completely sort of kills the predictability of the mining process. Maybe some block will be mined in 10 minutes, another block might take 30 minutes, 1 hour, and things like that. So we don't want to do that. And even if you were okay with that, it's not even clear how to implement it, right? Because let's say after 10 minutes you move on to the next person, and then the previous person shows up just right at the end of the interval. Some miners believe that the previous person showed up in time and they would mine the next block. Some people will think that no, the previous person was late and hence we already moved on to the next best person. So in a decentralized setting, there's always a problem of consensus on everything. Whether a person is online or not, that's already a problem of consensus in itself. So the way we solve this problem is we have a committee. We don't choose a single person with the highest score. So you choose a committee of, you take the n highest scores, where n is some parameter which you can decide, and all these people are now part of the committee. And the assumption in many of the systems is that a majority of the committee picked in such a way will be honest as well as online. And then this committee will run what is known as a Byzantine agreement protocol. And this protocol allows this committee to agree on what the next block is going to be. Any questions so far? And yeah, by the way, another thing which I didn't mention is that the signature on the last block the signature scheme which you are using must be deterministic and unique. So I sign the last block, right? Suppose the signature scheme is randomized, just like encryption schemes. So we saw El Gamal, how that is randomized and so on. Then even if the message is fixed, I can continue generating many different signatures. And I can pick the signature which maximizes my random ID. So that's an attack in itself. And that's why many of the proof of stake schemes, they use what is known as a unique signature. Unique signature means that given a message, there only exists a single valid signature on that message. You don't have a degree of freedom in deciding what your signature is going to be. And the textbook RSA signature is already a unique signature because the signature is just m to the power d. There's no randomness, there's no, there's no degree of freedom.
But like Didn't we say that like if we have a signature of M1 and M2, we can generate the signature of M1 into M2 and these things?
Yeah, so that's why textbook RSA signature is not secure. But we also looked at a variant of that, which is you hash the message first, and then you raise it to the power D. So I think that's also a unique signature scheme. Definitely a deterministic signature scheme.
But in that, didn't we use the CRHF and
That used random oracles. The hash function was a random oracle.
okay, sorry.
There's another issue which you need to be careful about in proof of stake. And this is known as posterior corruptions. It doesn't happen in proof of work. And it's a very tricky problem to deal with. Okay, so let's say this is our proof of stake based blockchains. Okay, let's look at this block. So suppose there's a bunch of miners. Let's call it a set S. So here a set S has majority of the stake at this point. Okay, at a later point, all stake is sold. And now this set S has no stake in the system. The next step is S becomes corrupted. Okay, I sold all my stake, or my friends, me and my friends, we sold all our stake, and now we become malicious. Now what we can do is we can create a fork from this point onwards. So the next step is S creates a fork. Okay, so this is like a parallel universe. And in this fork, S still has the majority stake. If you have majority of the stake, you can proceed, you can create a fork. Now some new miner joins. And you have these two different versions of the proof of stake based blockchain. How do you determine which one is the correct one? That's now completely unclear. The way this problem is resolved in proof of work is that if you go back from this point onwards, if you want to create a fork, which is as long as the fork, which is as long as the main chain, then you continue to need majority of the computing power. So creating a fork is very expensive in proof of work. But in proof of stake, I just go back to this point. I have majority of the stake, and I can create a chain, arbitrarily long chain. It doesn't take much work. And in this chain or in this fork, I never sold any stake. And these two are, in some sense, hard to distinguish which one is real and which one is fake, which one came after the fact. So this is a tricky problem, and there are some solutions to it, but nothing which is like very simple and which just completely solves the problem. It's more of workarounds rather than solutions.
But won't this decrease the value of the currency itself? So S will never do that.
Well, why not? S already sold all the stake, right? I have zero. Uh,
Okay.
I have zero stake in the system now. If I can go back and I can get back my stake, even if it's worth less, I still have the incentive to do it.
Right.
Okay, any questions before we stop? And let me give you a pointer to an interesting paper. This is called SOK. Research Perspectives. And challenges for Bitcoin and cryptocurrencies. This is sort of a survey of the area which focuses more on the ongoing research and open problems. What are the challenges? What are the unsolved problems, and so on. Okay, so this basically finishes our series of lectures on blockchains, and on Wednesday we will start zero knowledge proofs.